In today's lesson, we're going to take a look at segment lengths in circles. So first of all, we're going to cover a couple definitions that we haven't talked about yet. The first is segments of a chord. So when we have two chords in a circle, each chord would be divided into two segments. So if we want to get a visual over here, if I have two segments or two chords, we're going to see that each chord is going to be divided into two separate segments. Next definition is a secant segment. So a segment that contains a chord and one endpoint outside the circle. So here we have a chord, which is going to extend beyond the circle, and then we'll have an endpoint that's somewhere on the outside of the circle. So when we look at that, we have the chord, which is the part that basically goes from side to side, and then we also have this piece on the outside. So that piece on the outside is what we call the external segment. So that's the part of the secant segment that's outside the circle. Or in other words, that's this portion right here. All right, now that we have those definitions, let's go ahead and let's start taking a look at some theorems and some examples. Theorem 1014, segments of a chords theorem. So if two chords intersect in the interior of a circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. So let's look at this circle here, which has some of these chords labeled for us. So with this, what we're saying is that we have two chords that are intersecting at a circle at point E. We're saying that the product of the lengths of the segments of one chord. So if we look at, say, chord AB, the segments would be AE and EB. So if we multiply those segments, it's going to be equal to the product of the segments of the other chord. So we look at chord CD, we look at the segments of that, we have CE and ED, and those products will be equal to each other. So let's take a look at an example applying that. So here we have two chords that are intersecting at point N. So we know that the product of those is going to be equal. The product of the segments is going to be equal. So if I look at JN, which is X plus 5, and I multiply that by the other segment of that chord, NK, which is X, I know it's going to be equal to the segments of the other chord, which are going to be X plus 3 and X plus 1. We'll go ahead and start multiplying this out to solve for X. So over here on the left, we're just going to distribute that X through. X times X is X squared. Then we have 5 times X, which is 5X. The other one we're going to distribute through, or if you remember FOIL, we're going to be doing that here. Remember, another way of multiplying out a binomial is you could do the box method and set up a 2x2 grid and multiply it out that way. So I'm going to use the distributive method, which I'm going to distribute that first part of that binomial to the other binomial. So we have X times X, which is X squared, X times 1, which is X. Then we'll distribute the second part of that first binomial to the second binomial. We have 3 times X, which is 3X, and then 3 times 1, which is 3. Let's combine like terms on the right. So X squared, X plus 3X would be 4X plus 3. We'll bring down the left side. Then we'll start solving. So I'm going to subtract X squared from both sides, which will eliminate that exponent. And then we'll subtract 4X from both sides to get X is equal to 3. So if we take a look, we want to then find the lengths of those segments. So if I look at Ln here, if X is 3, the length of that segment would be 6. Here we just have X, so the length of NK would just be 3. NM would have a length of 4. And then Jn would give us a length of 8. All right, let's go ahead and move over to the next page. So on the next page, we have our next theorem, which is the segments of secants theorem. If two secant segments share the same endpoint outside a circle, then the product of the lengths of one secant segment and its external segment equals the product of the lengths of the other secant segment and its external segment. So let's go ahead. Let's take a look at what this actually looks like. So we have two secant segments, EB and ED. So what we're saying is that the product of that secant segment, so if I look at BE, the product of that and its external segment. So we're just talking about the external portion of that, which would be AE. It's going to be equal to the product of the other secant segment, which is DE, times its external portion, external segment, which is CE. Let's take a look at an example to apply that. So here we want to find the value of x. So we're going to take secant segment PR, multiply it by its external segment, which is QR, and that's going to be equal to the other secant segment, which is TR, times its external segment, which is SR. So here we see PR is going to be the total of those two segments. So we have 4 and 6, which give us a total length of 10. So we have 10 times the external segment, which is 6. Then we have TR, which would be x plus 5. Make sure we have that in parentheses, multiplied by its external segment, which is 5. We'll go ahead and multiply, distribute, and start solving for x. So 10 times 6 is 60. Other side, we're going to distribute that 5 through to get 5x plus 25. If we go ahead and subtract 25 from both sides, 35 is equal to 5x. Dividing by 5 would give us x equal to 7. If we wanted to check, we could plug that back in here for x, and we see that in PR we have 10 times its external, which is 6. We get 60 there. If we look here, we have 7 plus 5, which would give us 12 for that secant segment, times its external segment, which is 5. And we see that those products are equal. So that kind of confirms that our value of x is in fact correct. There's two below. I want you to go ahead and try those on your own. So pause the video, work those out, and then play the video again to check your answers. All right, so number one, we have two chords which are intersecting at a point inside the circle. So we know that the product of those segments are going to be equal. So we know that x times 6 is going to be equal to 5 times 12. If I simplify that, x times 6 is 6x. 5 times 12 is 60. We divide by 6. We come up with x is equal to 10. In the second one, we have our secant segments here. So this one's x plus 7. This one would be 14. So we know that the secant segment x plus 7 times its external segment, which is 7, is equal to the other secant segment 14 times its external segment, which is 6. Distribute over here and multiply over here. We subtract and divide, and we come up with an x value of 5. Moving on to the next page. Segments of secants and tangents. So if a secant segment and a tangent segment share a common endpoint outside the circle, then the product of the lengths of the secant segment and its external segment, which is what we just looked at in that previous theorem, equals the square of the length of the tangent segment. And if you think about it, it kind of makes sense because with this, since it's just touching the exterior, it's not split into two parts. We just have one segment. So when we're looking at the previous ones, we were always multiplying the two parts. Since we don't have two parts here, we're just going to multiply it by itself. So if we look algebraically at this, we're saying that the secant segment DE times its external segment CE is going to be equal to our tangent segment AE squared. Let's take a look at an example applying that. So here we have our secant segment RT and then our tangent segment RQ. So we know that our secant segment here would be the sum of x and 12. So the product of that secant segment and its external segment is going to be equal to our tangent segment, which is 14 squared. Let's go ahead and distribute over on the left, and then we'll square on the right. So we have x squared plus 12x on the left. On the right, 14 squared, which is 196. Now with this equation, we're not going to be able to solve this like we were earlier because the x squared is not going to end up canceling out. So we won't be able to solve this like a regular linear equation. We're going to have to solve it like a quadratic equation. So this is going to bring back some algebra skills that we haven't talked about in a while. The first step in solving a quadratic equation is getting it equal to 0. So the first thing that we want to do is get rid of everything from one side. We'll do that by subtracting 196 from the right. So that on the right side, 196 minus 196, we get 0 over there on the right. On the left, while we won't be able to combine that 196 with anything, we will move it over there to the left, and we'll write it out. So x squared plus 12x minus 196 is equal to 0. At this point, we talked about 3 different ways to solve quadratic equations last year. The first way, we talked about factoring and then using the zero product property. Second way that we talked about was using the quadratic formula, which, if you remember it all, was x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So with that quadratic formula, we have a, b, and c. So a is the coefficient of x squared, b is the coefficient of x, c is the constant. So in this case, a would be 1, b would be 12, and c would be negative 196. We could plug all those values in and then do the computations to figure out what the two x values are. That is a very lengthy process, so we're not going to do that in this one. If we try to factor this, we're going to find out that it doesn't end up working. This is actually a prime trinomial, so we won't be able to factor this. So we're going to go ahead and use Desmos to solve this. I'm not going to show you on the screen here how to actually do that, but I will kind of talk you through it. So what you want to do is you want to go to Desmos, the calculator. You're going to type in y equals x squared plus 12x minus 196, and you should see the graph, you should see the parabola pop up on your screen. If it doesn't, you may need to zoom out since this is going to be a fairly large graph. And what we're looking for is we're looking for the x-intercepts. We're looking for where this graph crosses the x-axis. So if you do that, you're going to find out that it crosses the x-axis at 2 points. It crosses the x-axis at negative 21.3 roughly, and at 9.2 roughly. So we know that these are the two values of x that make this equation true. Now, when we think about what the value of x has to be in this situation, we know that it has to be positive since we're talking about a length. So that's going to eliminate this negative answer. So we're not even going to consider that. And we know that the value of x, or the length of rs, must be approximately 9.2. All right, let's go ahead and let's move down to the next one. So here again, we have a secant segment and a tangent segment. So we know that the product of that secant segment, which is x plus 6, and its external segment, which is x, is equal to the tangent segment, which is 8 squared. On the left side will distribute. So we have x squared and 6x. On the right side, we're squaring that 8 to get 64. Again, notice here's a quadratic that we're going to have to solve like a quadratic because that x squared is not going to end up canceling. So the first thing we want to do is get it equal to 0, so we're going to subtract 64 from both sides. Once we do that, again, we do have 3 options in how we want to solve this. This one, again, is not going to be able to be factored, so that is kind of ruled out. We could do the quadratic formula, but again, that's very time-consuming and lengthy. So let's just go back to that graph. Let's go back to Desmos, type in y equals x squared plus 6x minus 64, and identify our x-intercepts. When you do that, you should come up with x-intercepts of about negative 11.5 and about 5.5. Again, in this problem, because we are talking about a length, we know it needs to be positive, so we will eliminate our negative answer. And we know that the value of x, or jk, must be approximately 5.5. On to the last page and our last example. So you are standing at a point C, which is 45 feet from the Point State Park fountain in Pittsburgh, Pennsylvania. The distance from you to a point of tangency on the fountain is 105 feet. We want to find the distance CA, which is between you and your friend who's at point A. So you're standing right here, 45 feet away from the fountain. You know that the length between you and a point of tangency over here is going to be 105 feet. And you're trying to find out the distance from you to your friend who's on the opposite side of the fountain. So with this, if you notice, we do have a secant segment and a tangent segment. So we're going to go ahead and use that theorem that we just learned about. The part that we don't know here is AB, so I'm just going to label that as X since that's an unknown value. So we know that the product of that secant segment, which is X plus 45, times the exterior segment, which is 45, is going to be equal to our tangent segment of 105 squared. We're going to distribute, multiply, and start solving for X. So when we distribute over here, we have 45X. And then 45 squared is 2,025. On the other side, we have 105 squared, which is 11,025. Here we do just have a regular linear equation, so we can solve it like any other linear equation. We subtract 2025 from both sides. So 45x is equal to 9,000. Then we divide by 45, come up with x is equal to 200. So we know that this length here of AB is going to be 200 feet. So basically that's going to be the distance across the fountain is 200 feet. Now you were standing 45 feet away from the fountain. So when we look for the distance between you and your friend, we have to include that. So we know that the total distance between you and your friend is going to be the distance across the fountain of 200 feet, plus the distance from you to the fountain, which is 45 feet, and we come up with a total distance of 245 feet. All right, folks, that's it for your notes for today. Go ahead and do your classwork, and then when you finish that, you can get started on your homework. Please let me know if you have any questions. Have a great day.